Hello. All right, we're going to get started. All right, so thank you guys so much for coming out tonight. I'm Shinju, and I'm the person behind Dystopia Labs. This is Elena with Beanstalk, and Remco is right over yonder, and he's with 0x. So just to introduce everyone, I used to be the head of growth at Stellar, then Thunder and Solana, and now I'm consulting at Tezos. Dystopia's Labs is like this random side hustle I'm doing to help good projects run events. So yeah, this venue is provided by Solana. They're a layer 1 high performance protocol on testnet right now. And here's Elena.
Hello, I'm Elena. I started a project called Beanstalk, and it's a new privacy coin that aims to make privacy coins very easy to use.
Hi, I'm Remco. I'm currently working at 0x, researching scaling solutions for decentralized exchanges. I'll tell more about 0x in my slides, but my background is generally in cybersecurity, cryptography, and peer-to-peer algorithms.
Awesome. So here's our agenda for tonight. We already did the networking, and Elena's going to start with the presentation on zero knowledge proofs. Then Remco will speak, and then Elena will do the coding portion. And we'll try our best to stay on schedule, but if it goes over, just sorry, we're trying our best. And yeah, that's it.
Do you know what the internet is? Wi-Fi? Cool. Hello. So this is going to be a presentation about zero knowledge proofs, but we're also going to go through kind of history of cryptography and the progression of how these technologies kind of happened to get to where we are today. Who is this workshop for? So I started out trying to understand Vitalik's blogs on zk-SNARKs, and despite him having a ton of claps, I didn't actually understand what his blog was about. And so this is for people who are in the same boat of you've tried to maybe understand this stuff before and it still isn't clicking. Oh, sorry. All these slides are on my Twitter, as well as there's going to be a coding part, and so the GitHub page where all the code is also there as well. Yeah, it's going to be broken up into 2 parts. The first part is we're going to talk about some cryptography, and the second part is I'm going to show you how you can actually use SNARKs today. And so we're going to make basically a very simple smart contract that's going to have SNARKs involved for verification. Okay, cool. So what is a zero knowledge proof? And, someone's at the door. And it's the ability to prove honest computation. So one example is there was a math professor, and he was trying to figure out how to give a canonical example for what zero knowledge proofs are. And one day he was reading a book to his son. The book was Where's Waldo? And for people who are not familiar with the book, it's basically a picture book where there's a ton of people and Waldo is somewhere there, and you're supposed to find Waldo. And so the math professor realized that this is a perfect setup for a zero knowledge proof. He was able to spot Waldo, and his son didn't see where Waldo is. And so the father said, I know where Waldo is, and the son said, prove it. So we're like in a very perfect setup for a zero knowledge proof. And so what the professor did is he got a piece of paper and he covered the entire book with this piece of paper with a small hole in the middle such that it revealed where Waldo is, but it revealed nothing else. The son was not able to get any other information about where Waldo actually was. And so this is a kind of an example of a zero knowledge proof. The father was able to prove to his son that he has some knowledge about a solution without revealing the solution itself. So biggest misconception is that zero-knowledge proofs equals privacy. That is not true. Zero-knowledge proofs does not equal privacy, and so I'll go over the different kinds of zero-knowledge proofs and different projects that use them for various things. What zero-knowledge proofs are is honest computation. So basically, I can say, I did some work. Let's say the function is f of x, and the result is y. And I can give you a proof that given some x, the result is y, but nothing else. And this is actually very powerful. So I can say I've done the computation of syncing the blockchain. So for example, for Bitcoin, when a miner goes and actually syncs the blocks, the reason why your CPU might be at 100% is because you're first of all verifying transactions, but second of all, you're putting them in your global state, meaning that I see like Jill sent money to Mark sent money to Alice, and so I'm updating my global state. So with a zero-knowledge proof, you can say, well, I've done the computation for this entire blockchain, and I can tell you everyone's balance, and I can just give you this very tiny proof for you to check very quickly that this state is correct. And that's one application. The other application is privacy. So I can say, well, there are a bunch of commitment notes. So imagine like a bunch of $100 bills on the table, and I can come up to you and say, one of these is mine, and I'm transferring the ownership of my $100 bill to somebody else. So you can also do that with a zero-knowledge proof, and that's how you get private transactions. So brief history of how actually this happened. So zero-knowledge proofs is not a new concept. In fact, they were first published about 1985 by a professor named Shafi Goldwasser and her colleagues. And they got tons of prizes for it and got heavy recognition for it. And so they kind of started off this trend of zero-knowledge proofs. And right now we have three main ones. So we have SNARKs, which are used in projects like Zcash. We have STARKs, which are kind of the new hotness, and Starkware is an entire company that resulted just because of STARKs. And then we have Bulletproofs. And so if you've heard about these zero-knowledge proofs before, or these zero-knowledge proof systems before, this is kind of how they compare between one another. So SNARKs are known for their small proof size. Their prover time is not the best. STARKs are known for very fast prover time, but their proof size is definitely not the best. And Bulletproofs are good for some things, but not others. They're really good for range proofs, and Monero actually uses them, but they're not good for prover time or verification time. So to give you kind of numbers to these colors, SNARK proof is super tiny. It's 288 bytes. But it does take 2.3 seconds to compute. And this is basically if you were to make a Zcash transaction with a considerable amount of constraints. This is kind of the rough metrics of what it would take to make a Zcash transaction with these different types of proofs. So SNARKs are basically, Zcash is the most popular company that I know of that uses SNARKs. And SNARKs do have what's called a trusted setup. So meaning that when the system first begins, there is a private key that needs to be thrown away, so to speak. And I'll actually explain to you what that means a bit later. So yeah, they actually have a really neat multi-party computation ceremony to basically have this trusted setup. SNARKs are also actually used in Coda, and Coda is a project that aims to do exactly what I described before, to basically compress, so to speak, the blockchain and say, you know, I've done the computation, this is the state of the world, and I can give you the small proof such that a new miner doesn't have to sync from the Genesis node. Bulletproofs are used in Monero. The biggest misconception is that even though bulletproofs are zero-knowledge proofs, they're not used for privacy in Monero. Ring signatures are used for privacy in Monero. But bulletproofs basically were a much more efficient range proof for them, and so they were able to have their transaction drop 80% in size just because they used a different zero-knowledge proof. And then 0x uses STARKs, and Remco is going to explain a bit more. But it basically allows them to do much more efficient transactions. And I won't steal his thunder. So there's tons of open source projects that actually contribute a ton of work. So if you want to get your hands dirty, there's a ton of open source libraries that you can use today. For SNARKs, we have probably the biggest kind of variation. So Zokrates is one that I'll show you today. Bellman is this incredible Rust implementation made by the Zcash team. SNARKs is made by Coda, so it's the OCaml representation. And all these slides are online, so this presentation is meant for you to kind of go back and click on some of these slides and kind of explore more. One snark library that I personally try to use myself is Circum, which is the idin3's library. It's the only one that I know that actually runs in browser, which is pretty awesome. Cool, so I'm going to explain to you a little bit how this cryptography works. So first is modular math. Modular math is fairly simple. It basically says, let's imagine that my world is bound into like this particular thing. So if anyone's familiar with computer science terms, it's basically the mod symbol. So if I were to do 22 mod 12, it would basically wrap around, and I would get 10. So the first one is Dittie Hellman. Dittie Hellman is kind of this amazing story. So I think Hellman was the guy who was obsessed with this problem of, let's say I wanted to send an encrypted message to a friend of mine. So I send them this encrypted message, but how do I send them the decryption key? Well, I guess I can encrypt the decryption key, but then it becomes a recursive problem. How do I send them the key to decrypt the decryption key? And so he was obsessed with this problem. How do I share a secret such that I can send a secret over the wire, like over a public channel, and have that message be secure? And so he teamed up with this guy named Diffie, and he drove basically across country to meet him, I think at Stanford, and it took them, I think, 4 years roughly to come up with this pretty neat algorithm. So this is how Dittie Hellman works, and let's say I wanted to encrypt a message and send it over to a friend of mine. How would I get a shared secret, meaning the encryption key itself? How would I give that to a friend of mine such that no one else can retrieve it? So first there's a setup phase. So we're going to have these two numbers, P and G. And so let's say I'm Alice and I decide to choose a private key, so to speak. So my secret is going to be A, and A equals 4. And I can compute basically a public key, because what I'm taking is I'm taking my base, G, which is 5, and raising it to my private key. And I get my public key, basically. And my public key I can share with anyone. So I share it over the wire. Bob gets my public key. And then Bob does the same thing. So Bob also has a private and public key. And so now, because each party has the other's public key, they actually have enough information to compute a shared secret. So what Alice does is she takes Bob's public key and uses her private key to come up with the number 18. And Bob actually has the same information. So Bob uses his private key and Alice's public key to come up with the same number, which is 18. And now they can use 18 as the encryption key for their message. So the next one is RSA. And RSA was a build-up on Dittie Hellman. So now we have something more interesting. We have digital signatures. And it's a very similar approach. There's also a setup. Now we have 2 primes. And we use these 2 primes to calculate the totient. So basically, you take these 2 primes, you find the least common multiplier. And here we have a similar system where now we have a bound, or basically a constraint system for us to choose a private key. So for this example, my private key is 3. And I can also choose a public key. So in this example, my public key would be 11. And now if I wanted to sign a message, let's say the message that I wanted to sign is 2, all I have to do is raise 2 to my private key, and I get 8, and anyone can verify using my public key that I indeed signed this message 2. So pretty awesome. And then we have Fiat Shamir, which is actually like the grandfather for zero-knowledge proofs. So they take this concept and they take it much further. So basically, I want to prove that I know the pre-image of x. Let's say we have this hashing function where if I know x, I raise g to the x, and that's basically kind of like my hash function. And I'm trying to prove to you that I know x before it was essentially hashed, so the pre-image of x. So what I do is, okay, so I choose a different random number, v, and I send t such that t equals g to the v. And Bob chooses another random C and sends that to Alice. And she sends back a different number. So she uses V that she calculated before, and she basically sends back R, which is V minus CX. So Bob can now check that T equals G to the R, Y to the C. I kind of tried to color code this. So basically this is very basic like equality checks. And now we can say, okay, well, R equals V minus CX. So when we're trying to do G to the R, and we know what R equals to, we can replace that. And we know what Y equals to from equals G to the X, so we can replace that, and we have an equality check. And basically, what I want you to get out of this slide is that Alice was basically able to prove that she knows the preimage of X by sending different numbers that such that they check this equality. So that's pretty cool. But here's something cooler. So then, like a bit further down the line, elliptic cryptography got kind of more attention. And I want to explain to you kind of how it works and why it's such a cool topic right now. So most of this I took from this other great tutorial. So if you have these slides later, please check out this tutorial if you really wanted to go over them in detail. So elliptic curve cryptography sounds really complex, but elliptic curves actually all follow this formula. So it's actually not as complex as you might think. The cool thing about it is that if you ever see an HTTPS website, which at this point is actually every website, you're basically using elliptic curve cryptography. So basically 3/4 of the 100,000 top websites use what's called ECDHE, so elliptic curve Dittie Hellman exchange, and 96% of those use actually a very particular curve that is recommended by the NIST standard. So there's actually some NSA conspiracy theory because they were highly recommended from the seed that no one knows how it came about. So you can read about that also. Okay, so there's something called an abelian group. An abelian group basically means, okay, we're going to define saneness. So we're going to define some things that we're very familiar with math. So we know what the identity property is. So if I add something, if I add 0 to something, I get that number back. I know what the inverse property means, meaning that for a plus b equals 0, meaning that a minus b must also equal 0, or sorry, a equals b. We have commutativity, which is a word I can never pronounce, basically meaning that if a plus b equals b plus a, so we can flip those. So for elliptic curve cryptography, we have the same properties. So let's say we have 3 aligned points, and we can say p plus q plus r equals 0. And that's actually how it looks like. So this is an elliptic curve, and we have 3 points, and we can say that they have this property. And now, if p plus q plus r equals 0, then p plus q must equal negative r. So now we have a way to add 2 points. That's pretty cool. So the way you add 2 points is basically, if you're familiar with like algebra from middle school or high school, just because it's an elliptic curve, it doesn't actually change any properties. It works about the same way. So here we can say if p is this point 1, 2 on this particular curve, then we can add p plus p together. And p plus p on this particular curve would equal -1, -4. Cool, so, and I can actually show you how it looks like. So this is p plus q, p plus p equals -r. So here we have p equals q, and so those 2 particular points do indeed equal to -1, -4. Okay, so if we can add p plus p together, we can do it n times. So we can basically do the same operation n times. And we have like various methods to how to make this really quick. So now we have a method of doing n times p on an elliptic curve. And even though n times p might be really easy to compute, or at least we have really fast methods to compute it, going the other way around, meaning dividing, is nearly impossible. And it's called the logarithm problem. And it's really confusing because it really should be called the division problem, but for conformity reasons, they called it the logarithm problem. Kind of confusing for no reason. But one thing that we are missing is we're missing cycle. So if you remember, the reason why Dittie Hellman worked, the reason why Fiat-Shamir worked, the reason why RSA worked is because we have a finite field. And this really crazy math works because we can wrap around certain n times to get to a different point. So how do we have the same property here? Well, we can do the same thing. We can actually mod everything again. So the same property that we've seen for Dittie Hellman, we can actually apply to elliptic curves as well. So now, if we were to take the same curve that you've seen before and apply it, we'll bind it to a finite field, it'll look a lot different. So if we say that our finite field is 19, and you almost always want to take a prime number, otherwise you get some really weird curves, then your curve becomes a bit less interesting, but this is kind of how it would look like. Okay, so we could do p plus p before. Can we do p plus p on a finite field? And if you remember from our from the previous slide, we got that p plus p equals -1, -4. Well, we could just take and mod. We could take it and basically bind it to that field, and we would get a different point, 18, 15. It's actually as easy as that. And to prove it to you, there's another illustration of how now we have p plus p on a finite field would equal this 18, 15, which is a different point. Okay, cool. So now can we do multiplication in a finite field? And here's a pretty cool property. So let's say we're trying to multiply p, which is our point. Here it's 3, 6. We're trying to multiply it by 0. Okay, we get 0. Now we're going to try and multiply it by 1. So there's my point over there. 2, 3, 4, 5. Oh, look, 5 is the same as it was 0. 6 is the same as it was when n equals 1. 7, 8, 9. And so what we see here is that we have a cycle. So when we took a curve and we took a generator point, p, and we started multiplying it n times, what we've seen is that this particular point has 5 distinct points. No matter how big n is, it'll always be one of these 3 distinct points. And so here we can say that these 5 points are closed under addition. So no matter how much you add them, you're going to get a point that's one of these 5. And so here we say that this is the order of a subgroup, where our point P is the generator or base point, and here we have an order of 5, meaning that no matter how you multiply this generator point, it's going to be always one of the 5 points. And we have the same properties here too. N times p is pretty easy, but n or p divided by q is nearly impossible. And this is actually exactly how ECDSA signature scheme works. So n is your private key, p is a generator point, and the result of that is your public key. So the cool thing about that, basically for ECDSA, which is how Bitcoin works, and Ethereum, and many others, all you have to do is you have to multiply your private key by a generator point, and you get your public key. The super cool thing about it is if you were to do that with RSA, you would need 3092 bit length key. But for Bitcoin, it's only 256 bits. And so it's a much more efficient way for us to do signature schemes. Okay, so then, now that we know we can multiply things, can we go further? So there's something called a Pedersen hash, or a Pedersen commitment, and there's a project called Grin, if you're familiar with that. It's a privacy coin, and they basically took the concept of a Pedersen commitment and totally ran with it. So basically, there's a problem where, let's say I have common denominations of a currency, let's say like $1 bill, $5 bill, etc. Then even though I'm multiplying it by a generator point, and even though I can't divide and I can't go back, I can do like what's called a rainbow attack, like meaning I can just pre-compute all the most common denominations and just have like a lookup table. So I can't divide, but I can at least have like a brute force way of doing it. So for something like a currency, you might want to hide that a bit better. So what they've done is basically now you have a blinding factor. So you have, let's say, some value, like $1 times a generator point. So we've seen that before. And now we have a blinding factor. Now the cool thing about this property is that even though the result of this is very hard to go back, meaning that division is fairly impossible, but we can do really cool stuff with it. It still operates on the basis of math, so we can still have equality. Even though we may not be able to know what these specific values are, we're still able to do commutative property with that. So basically add the two things that are multiplied by g, and we can check certain equality conditions. Okay, so actually bulletproofs work with Pedersen commitments really well. So the point of bulletproofs is basically have zero knowledge of the inner product of two vectors, which sounds really complex, but if you're in computer science here at all, basically what I'm trying to say is any number can be represented in its decimal form. So for example, 5 can be represented as 101. And the reason why 101 in binary equals 5 in decimal is because we know that the digits represent what base it is in base 2. So 5 basically equals 1 times 2 to the second plus 0 times 2 to the first plus 1 times 2 to the 0th. And that's why 5 equals 101 in binary. So basically, the concept of bulletproofs is you're saying I can represent any number as an inner product of these two vectors, and if 5 is 101, that means I need at least 3 bits to represent this number. And if I can prove that this number needs at least 3 bits to be represented, then I can also prove that it falls in the range of 0 to 2 to the n, because 2 to the n would be the max. So here 2 to the n would be 8. So basically it's me saying I can prove that I have this number and it's between the range of 0 to 8, and it's 5. But I don't need to tell you that it's 5. So yeah, this is basically how bulletproofs work, and it's actually very similar to Fiat-Shamir, so kind of the grandfather of zero-knowledge proofs. And if you've ever seen this really crazy schematic, this is actually bulletproofs in one slide. And the Chain Interstellar team have a great documentation about bulletproofs, so I really highly encourage you to go and actually, if you're interested, to kind of go and explore this a bit further, because they have really good documentation. So there's a link for that. Okay, so next up is SNARKs, and we have Remco, who's basically an expert, so I'll kind of leave that to him. But next up is SNARKs. So I had a water here, but it's gone now. There's actually lots of variations of SNARKs. So I'm going to show you just one variation, but if there are people, who are there's like tons of effort going in the space of SNARK, so I don't want to insult anyone by kind of disregarding the work. So yeah, I'm going to show you what's called the CAP variant, and it's basically a way for you to go from computation to a circuit to rank 1 constraint system to what's called a CAP, quadratic arithmetic program, and then finally to a SNARK. So there's a tutorial by Decentric, which is actually really good if you wanted to kind of dive more into this, and these slides are going to be fully available. Okay, so let's say I have an equation, and the equation is x times y plus 4 equals 10. And somehow I want to prove to you that I know x and y, but I don't want to tell you what x and y are. So the first step is I'm going to break this into what's called an arithmetic circuit. So I'm going to flatten this program of how it's represented as terms of gates. So here we have x times y going into the first gate. They're going to have a temporary output going into the second gate. So basically what we're trying to achieve is we're trying to say we're going to break it into x times y, and then we're going to add that temporary variable to 4, and then finally we're going to check the equality constraint. So here for x times y equals 4, we're going to have what's called 2 constraints, or 2 gates. So for any of these constraints, we're going to have just one property we're going to always maintain, and it's that left times right equals output. So for example, for our first constraint, it's x times y equals temporary output. And then for the second gate, we have addition, but we're going to cheat and we're going to multiply it by 1. So it's always left times right equals output. And basically what we do here is then we're going to go from this arithmetic circuit to a language of polynomials. So how do we do that? So we're first going to represent our variable vector. So our variable vector is all the variables we need to represent what a SNARK is. So here we have x, y. We need a temporary variable for output 1. And then we're going to have one like a placeholder for constants. So basically for the first one, we want to represent the statement x times y equals output. And so basically what we do is we take our variable vector and say, okay, so for left we have, we want to get to x. So if you multiply 0, 1, 0, 0 by our variable vector, you're going to get x. To get y, we're going to have 0, 0, 1, 0. So basically we will multiply that by the variable vector. And for to represent the temporary variable, we'll just have 0, 0, 1. So basically, you have all this, and your goal is to get to polynomials. So now we actually have two constraints that have these set of points, and we can use these points to represent a polynomial. Because now, for the left constraint, we have 2 points. In the first constraint, basically we have a point 0, 0, or sorry, like 1, 0 equals 0. And for the second one, the first point is 4. So we have 2 points. We have 1, 0 and 2, 4. And we're basically able to create a polynomial for the left variable, so the left wires. And then similarly, we're able to make a polynomial for the right wires. So kind of the nitty-gritty work. So for the left constraints alone, this would be the set of polynomials for that SNARK. And basically what we want to do is we want to always have this equality, that left times right equals output. And we're going to have that forever. So now we have if left times right equals output, then left times right minus output equals kind of our overarching polynomial. So we have this one polynomial to represent everything, and we're going to say, okay, now that we have this polynomial, that L times R minus O, it can be divided by something else, such as T, which is kind of known by everyone. And the verifier also needs to give me the thing that makes this equation have like an equality. So even though we have L times R minus O, and we're basically trying to prove that this can be divided by something else, by another polynomial, such that the T, which is publicly known, makes this all work out. So now we say, okay, so the prover needs to evaluate something on their polynomials. Now the problem is, for the verifier, you want to basically make it such that the thing that you're trying to evaluate is hidden. Because the problem is, let's say I have my polynomial, and the person who's challenging me gives me a challenge, but I can kind of fake my output. So if I know the challenge beforehand, I can say, okay, I don't actually need to use any of my polynomials. I know exactly how you're going to verify me. So knowing the challenge beforehand, I can fake a proof. So then the challenge becomes, okay, how do you make this challenge such that it actually forces the prover to run this challenge through their polynomials? And one way to do that is to actually encrypt the challenge itself. So you have these polynomials, and you're trying to pass this number x for them, this value x for them to actually evaluate it, but we're going to encrypt x. So now it's kind of crazy. Okay, so we have this linear combination of challenges, and now we're actually going to encrypt them. And the reason why it works is because of homomorphic addition. So kind of like Pedersen hashes before, where even though these numbers are encrypted, we can still do operations on them. This is the same concept here. And so even though these things are encrypted, we can still be able to answer this challenge of L times R minus O equals T, which is kind of a hard-coded number, times H and S. So basically now we have a system for a challenger to send a challenge encrypted such that the verifier, or such that the prover doesn't know it beforehand, and they're forced to basically use their polynomial to answer back because there's no way for you to make a proof now. So, okay, but now we kind of described a very interactive example. So for the challenger to keep sending this challenge, you would have to basically have a new S, or like new secret challenge per round. But we're able to solve this by actually encrypting S. So the question is, who knows what S was plain text? So who knows what S was before it got encrypted? And S actually here is what's the part of the trusted setup of a snark. So if you have ever heard Zcash talking about toxic waste and how they promise to throw away toxic waste, what they're actually talking about is they have a setup for this challenge that's actually hard-coded in the entire system, and it's okay that it's hard-coded because it's encrypted, and the actual seed, the actual secret that was used to generate this is thrown away. Yeah, and so the reason why we're able to do operations on this, despite the fact that it's encrypted, is because of the fact that we can do math on elliptic curves. So we can add points even though they're still encrypted because we can't divide. Cool, so an example of that is, let's say we have a function that encrypts things, like if I multiply something by E, or like we have a function E, then even though I don't know 3 and 4, I can still do this operation, and I can come out with an answer that's still encrypted. So basically, even though 3 and 4 are both encrypted, I can still do addition on them to come up with an answer. So back to the actual snark, the thing that makes this all work is that the prover just needs to prove that they've evaluated their polynomials such that L times R minus O equals T times H. And the way I'm able to do that is I'm able to evaluate that secret number that's encrypted and send back my answer in its encrypted form. So the way we make it zero knowledge is that we also add a blinding factor to all of this, so that no assignment is actually leaked. So to make it zero knowledge is fairly trivial, and you're basically adding a blinding factor, but you still always have this equality of L times R minus O equals T times H. So to kind of tie this all together, because I know it's kind of a lot, you're basically saying, okay, first I'm going to have a setup, meaning I need a challenge, and I need to encrypt this challenge. And I'm going to throw away the thing that I used to make this challenge. So the setup is that I computed S, I have E of S, so encrypted S, and I can hard code that, and then I would throw away the S itself. The prover has their polynomials, so L, R, O, and H, and the prover basically just needs to send the evaluation of the secret on their polynomials, and then anyone on the network can check the equality of L times R minus O equals H times T. So this is kind of an oversimplification, and there's a lot of great articles that go in depth in actually explaining this. This, what I just described, is called the Pinocchio protocol. So if you're familiar with Zcash, their first upgrade was called Sprout, and Sprout actually used this exact mechanism, so it's called the Pinocchio. There is a proving system that is kind of the standard now, and it's called Groth 16, and actually Zcash just moved to it in October. Cool, and so what's happening with SNARKs now? There's actually a ton of research in SNARKs right now. So most research facilities now are working on lattice-based SNARKs. So basically it's a way to condense this information further and make them a lot more efficient. There's a ton of research in pairings. So the reason why SNARKs take such a long time to compute is because you're trying to evaluate multiplication on elliptic curves, and that is a fairly expensive operation. So there's a ton of research going on right now of how to make multiplication a lot more efficient. Next up is going to be Remco, and then I'm going to show you how there's so many open source platforms that actually make it super easy for you to get started with SNARKs today. Yeah, and that's it.